Oh, sorry. Just, singing along to the old 70s song, breaking up is hard to do, which you would not really actually want to hear me sing. Yes, breaking up is hard to do, especially when you're a molecule, but it happens, especially when free radicals are involved. That's what we're going to talk about in chapter 25. This is a big intro overview before we segue back into chapter 16. So, free radicals, what the heck? What's up with that? Well, you've heard it from me enough. It's all electrophile meets nucleophile, right? Well, not always. Okay, so this is what we've seen for the entire O-Chem up to this point, all through first semester and including anything we've been talking about this semester. An electron-rich, maybe anionic nucleophile seeks out a electron-poor electrophile, and the two electrons, they join and make a bond right there, and that's chemistry. But what if you don't have a anion and a cation, or even a delta positive and a delta negative? Maybe it's not polar at all. Reactions can still happen. So this reaction, generic reaction, illustrates that very thing. That instead of having a 2-electron nucleophile and an electron-poor electrophile, what if my bond just cleaves in two, with one electron going to the X group and the other electron going to the Y group? That reaction is called homolysis. Lysis because the bond is breaking, homo because you're getting two of the same kind of reactive intermediate instead of an anion and a cation. So heterolysis gives us two different, homolysis gives us two of the same. They're both radicals, a single unpaired electron. So one thing to point out here is that there is now a new arrow on the block. Note that when we're talking about two electrons moving, as in the bottom example, we use our typical old double-headed arrow. But if we're interested in homolysis, where, as we've shown, the two electrons in that sigma bond each go to either the X or the Y, then we use what we call a fishhook, a single-headed arrow. So pay attention as you draw mechanisms for radical chemistry that you use the proper arrow. Now, why would this happen? Well, if you look at the tables on page 1202 and 1203, which are full of very useful information, you'll see that there are actually quite a few molecules that are pretty susceptible to homolysis. So, for example, bromine itself. The bromine-bromine bond is not very strong, and it's pretty easy, given enough energy, for it to fragment homolytically to give you two bromine radicals. Similarly, we've already seen just how energetic a peroxide is. My goodness, to break this peroxy acetate here, piece of cake. All it takes is 123 kilojoules. So for some molecules, it's very easy to have homolytic cleavage take place with just a little heat or perhaps light of the right wavelength. So that's all it takes. And this is your kind of your dead giveaway that we're talking about radical chemistry. If the reagent, quote unquote, over the arrow, there's no acid, there's no base, there's nothing polar at all, it's just H nu signifying light of a particular wavelength, or heat, That's all it takes to break these super weak bonds and generate a radical. What's complex, tricky, and confusing about radical chemistry is that it may seem totally random. Like, gee whiz, what bond can break? Any bond can break. Just pick a bond, any bond. It's not that random. And we'll spend all of our effort trying to understand where the radical is most likely to form. This is particularly important in mass spec, which we'll get back to in chapter 16. So where is the radical most likely to form? Well, it's going to depend on the stability of the radical that's formed. So this molecule is N-bromosuccinimide, abbreviated NBS, and NBS has a particularly weak bond between the nitrogen and the bromine. So it's not difficult at all for, upon the addition of just a little bit of heat, homolytic cleavage to take place, two fishhook arrows signifying that I end up with one electron on my bromine and one electron on my nitrogen, so I have generated two radicals. Why should that radical be so easily formed? Well, basically, it's because of our good friend resonance. So I can delocalize that unpaired electron just like I've delocalized two electrons. They just need to be shared by next door neighbors, and in so doing, basically what I end up with is, oops, not that, a delocalized radical that is shared by both the nitrogen and the oxygen. And in fact, of course, we can go ahead and delocalize that guy back down again to get the initial resonance contributor, and of course I can delocalize that into the other carbonyl as well. So delocalization of that radical makes it particularly stable. So it makes sense that that would be easily formed. How about in this case? What we're showing is that for this allylic system, just shine light of the right wavelength on one propene, just propene, and then what do you got? Well, you managed to generate the radical right there on that carbon. So what happened? Well, we just basically lost the hydrogen radical. Well, gee whiz, we got hydrogens here, we got hydrogens here. Why would it be one of these hydrogens? Well, because again, we've got delocalization that can take place so that this particular allyl radical, just like the allyl cation or the allyl anion, can be delocalized. Oh, that was funky. Try that again. There we go. We end up delocalizing the radical onto two carbons, not just one. So both this carbon and this carbon share that unpaired electron when you look at the resonance hybrid. And since carbon, of course, wants 8 electrons, it wants to have 4 bonds, the unpaired radical species, that's not particularly stable. It's electron poor, and so anything that we can do to share that electron poor spot in a molecule is going to stabilize it. So, makes sense. Resonance delocalization can stabilize radicals just as well as cations and anions. Well, now let's compare the allyl radical to just the plain old-fashioned propyl radical. Propyl radical can't delocalize that odd electron anywhere, so it's remarkably unstable. Well, how about this guy, the butyl radical, where the radical is localized on a secondary carbon. This guy, primary carbon. If you remember carbocation stability, you remember that alkyl groups are electron releasing. So the more electron releasing alkyl groups there are around this electron poor carbon, the more stable it's going to be. So just as for carbocations, a tertiary radical, this guy here, with 3 electron releasing alkyl groups donating electron density into the carbon radical, that's going to be more stable than a secondary radical, and the primary radical is going to be the least stable. But wait, isn't this a primary radical? Yes, it is, but resonance trumps all. The allyl radical is much, much, much more stable than the undelocalized primary radical. So what we're showing you here is stuff that you already know. The same features that we've used all along to explain acid-base strength, carbocation stability, they work for understanding the stability of radicals as well. Now, what do they do? What do radicals do? Well, they're highly reactive species. They're electron poor. Like I said, carbon wants to have 4 bonds, wants to have 8 electrons. So when you have a radical, it would be thrilled to couple with another radical. So for example, if I have the allyl radical and it's floating around in a sea in a beaker of other things that include a bromine radical, then it's going to be very easy for those two to find each other and make a new bond. So that's what those 2 electron movement arrows signify, that the product of this particular step, this coupling step, is actually making a new bond right here between this carbon and this bromine. So it kind of looks like they're joining in midair, but I can't really animate this. The bromine and the allyl radical are moving towards one another, and when they get close enough together they couple, making a new sp3 sp3 sigma bond. So that's pretty impressive, because what we've got here are 2 really high energy intermediates that are reacting. There is no energy barrier whatsoever. So these are my radicals. Here's my product. Totally exothermic for a coupling reaction. No energy barrier. So Carty talks about another elementary step associated with radicals, that being bimolecular homolytic substitution, which is a mouthful. We're just going to call it atom transfer. So for atom transfer, all we're doing is seeing one radical react with something that's not a radical, and in so doing it will transfer an atom. So for example, hydrogen atom abstraction is a very, very common radical process. So this is toluene. If toluene happens to encounter a chlorine radical, then the chlorine radical will say, can I transfer an atom from that toluene and make a nice stable radical? And of course it can, if it abstracts one of those 3 methyl hydrogens, then what do we have? We have a benzyl radical that can really be delocalized right there. So that can get delocalized all throughout the ring, and I would certainly encourage you to draw the resonance contributors. But basically, this is an example of atom transfer, and it's an illustration of how the most stable radical is going to be formed. Obviously, the other product in this step is HCl. Alright, so radicals couple. Radicals can react with non-radical species and just transfer an atom, or a third example of what radicals can do is something called combination, where they actually react with the electron-rich pi molecular orbital. So remember, this is all driven by the fact that radicals are electron poor. They're looking for something electron-rich. What do we have here? We have a nice little pot of electron density right there in that pi bond. So we can do a homolytic splitting of the pi bond like so to give us a new radical on that left-hand carbon. And what these 2 orange arrows are signifying is that I'm making a new bond between the right-hand carbon and this tin piece. And then we'll leave our hydrogens alone, they weren't involved. So here's my new bond, but I've just added the 2 pieces together. I've combined them, and I generate a new radical species right there. So those are the 3 elementary steps for radical chemistry. And again, I want to stress that radicals are much like carbocations or any other kind of electrophile. It's electron poor, and it's just looking for something to hook up with in such a way that the most stable radical will form in that elementary step. Alright, so in chapter 25 we will look at 3 reactions. Well, we may look at more than 3 reactions actually. We'll initially look at 3 reactions. The radical halogenation of alkanes is kind of the basic radical reaction. We'll look at allylic bromination, and we will look at another anti-Markovnikov reaction. Very nice to have this in your synthetic toolbox. So instead of hydroboration being the only thing you know that will give you anti-Markovnikov addition, we now will see how we can add HBr to an alkene and get anti-Markovnikov addition. At some point we will segue back to chapter 16, because mass spectroscopy is absolute voodoo unless you understand radical chemistry. So that's it for the intro, but an important question: what did the Mexican fireman name his 2 sons? Got it? Jose and Jose. I love that one. Yeah, okay. See you in class.